Okay, hello everyone. We'll continue shortly. As usual, please write your name on the chat area so that I can see that you're here. And we'll continue right where we left off. So we were talking about figuring out the areas of polar regions. And we figured out that it wasn't that big of a deal. We could slice and dice using little angular slices, like little pizza slices that we could approximate with the sector area of a circle. And with that, we were able to get a formula for the area of a polar region. And the difficulty is to figure out the beginning at the end, mostly. The intervals are not that difficult. So let's pick it up where we left off. We were working on a problem, this one right over here. We have this cardioid, the cardioid 1 plus cosine theta, and the circle radius r equals 1. And we wanted to get this area that is inside the circle, but outside the cardioid. And the way we set it up was we're doing the area between two functions. One of them is this circle, and the other one is this cardioid. Like I explained last time, the circle is the outer function because it's the one that is farther away. You can see it on this ray. This point is the one that is farther away, the point on the circle, and the point on the cardioid is closer. So we need to get this area over here, and the formula is right here. Someone asked last time why I have 1/2 of the area, and the reason is I'm only going to do half of the area because it's easy to integrate from pi over 2 to pi. Alternatively, if you want, you can also do it from pi over 2 all the way to 3 pi over 2. That will work too. So it's just a matter of you know, choice and taste. I kind of like to use symmetry, so I'm doing 1/2 of the area, this part over here, only the top part, and that's this formula over here, the integral from pi over 2 to pi, the outer minus the inner. Here are the corresponding ones, and we set it up like this. So all we need to do now is figure out this integral, and that's where we're going to pick it up now. So first thing I'm going to do is cancel this 1/2. So the area that we're looking for will really be just this integral from pi over 2 to pi of, and we need to square, to expand this square. There's really no other way. So this is this one, and then minus 1 plus 2 cosine theta plus cosine squared theta d theta. And when we simplify it, so this 1 and this -1 go away. So my new integral is -2 cosine theta, negative cosine squared theta, d theta. And just as we did it for one problem last class, the way we deal with cosine square is by using the half angle identity. So for the half angle identity, what we need to do is we need to write down cosine square. We need to put it over here. So we call that cosine squared theta is cosine of twice the angle plus 1 divided by 2. That's how we do it. Right? So that's what we're going to put in here. Integral from pi over 2 to pi, -2 cosine theta, and then minus cosine 2 theta plus 1 divided by 2. Right, and I think we're ready to integrate. Let me just clean it up a little bit before we do that. So let's put the constant first. It would be -1/2 minus 2 cosine theta minus 1/2 of cosine 2 theta. Everything is negative. That's okay. So now let's integrate. It will be -1/2 theta. Then the integral of cosine theta is sine theta. And then the integral of cosine 2 theta is sine 2 theta over 2. So this is -1/4 sine 2 theta. And we're supposed to evaluate this from pi over 2 to a pi. All right? Let's carry it out. So it will be negative a half of pi minus 2 times sine of pi minus 1/4 sine of 2 pi minus, and then plug pi over 2, negative a half of pi over 2 minus 2 sine of pi over 2 minus 1/4 sine of pi. Okay, and ordinarily, as you know from our class, you could stop and leave the answer right here. But I'm curious because since we have the negative signs, I just want to make sure that our answer is actually a positive number, right? Because we represent some area. If you get a negative number, then there's definitely something wrong here. So let's take a look at how this simplifies. So sine of pi is 0, so this guy is 0. That guy is 0. Sine of 2 pi is also 0. This is 0. This guy is 1, right? And I think that's about it. So let's see what we get. We get negative pi over 2 minus, and then this is negative pi over 4, and this is negative 2. And that's it. The rest of the quantities here are 0, right? All these other ones that are marked are 0. So then for the remaining, what we get is, let's see, this is positive 2. And then we have positive pi over 4 minus pi over 2, so that's negative pi over 4. Right, and pi is about 3.1 something, so this is less than 1. So this number is indeed positive, right? And that gives me tranquility, right? A peace of mind. We got a number that is actually a positive number. So that's actually fine. All right, questions? Okay, let's do another problem. Next one. Okay, so let's go to the book. Where's the book? Right here. Okay, and so this is the one we just did. We did this light blue shaded area that you see on the screen right now. That's the part we calculated. And next, what we're going to do is look at the next problem. So I think it's on the next page. Yeah, so this part B is the one we just did, 2 minus pi over 4. I'm not doing part A because part A can be simply done. If I were to ask to do part A was a complementary region inside the circle and inside the cardioid. The best way to do that one right now is just to take the area of the circle and subtract the light blue area we just calculated, and then that would be the answer. So it's not worth it, in my opinion, to do part A. Instead, I want to do example 6, which is on next page. So let's go to next page and do example 6. So we're still going to have two curves. This time, again, a circle and a cardioid, although now the circle is a little bit different. And there's a variety of problems here. So let's figure out, let me show you the graph right there. So we have the cardioid, the same cardioid, 1 plus cosine theta. And we have this circle, 3 cosine theta. Is this black circle. And then the example asks us to figure out all of these regions, region A, region B, and region C, okay? So I'm going to do it from scratch because this picture helps a lot, all right? So if you have the picture, it's already a huge help. So let's imagine that we don't have the picture, or we have a generic picture. We don't know where the points intersect. And that's how we're gonna do it, all right? So this is example 6, and let's start with part A. So we have two regions. One of them is in two curves. One of them is our regular cardioid, our axis here, and we have 1 and 2 here, and this is our cardioid, r equals 1 plus cosine theta. And we also have the circle. The circle is 3 cosine theta, so we go 3 units this way. So it's a circle of radius 1.5. All right. And first question we want to do is region A. What is this area? So find the area of region A. And oh, remember, this blue circle is has a polar equation 3 cosine theta. Okay, so first task.
Verizon Wireless, your call cannot be completed as the called party is temporarily unavailable.
First task here is, let's see, whose microphone was that? I don't know. So our first task here is to figure out these points of intersection, right? Because let's figure it out. To get this area over here, we need to find out these angles, right? We need to find out from where is it that we're gonna begin our integral and where is it that we're gonna end our integral, these two rays that I just drew, right? So this one is kind of clear, it's just the origin, right? Is angle 0. But this one, we don't know. So our first goal is to figure out that point. And to figure out where two curves intersect, you do the same thing you do with regular rectangular coordinates. You just figure out an equation. So this point should satisfy both equations. So the way to find out the angle is to set this up equal to each other. So to find the point of intersection, the points of intersection, set the two equations equal to each other. And so that would be 1 plus cosine theta and 3 cosine theta, right? And then we can solve for theta here. So this, putting this cosine on this way, it will be 2 cosine theta equals 1, or this means cosine theta equals 1/2. And then you ask yourself, what are the angles that have a cosine between a cosine of 1/2? And the answer is 60 degrees, right? Or pi over 3. Or 2 pi, or negative pi over 3, that will work too, or or pi over 3 plus more turns, any of those. So theta equals pi over 3 and theta equals negative pi over 3 work if you, and those correspond to these points now. So this is when theta is pi over 3, and this is when theta is negative pi over 3. We discover them, right? Now, you may have noticed that we didn't capture this other intersection, the origin. And the origin is a difficult one to capture because the origin you may get when the radius is 0. And when the radius is 0, the angle could be whatever, right? You could have any angle with r equals 0, and that would give you this point. So this method of setting the equations equal to each other, it doesn't work all the time, right? It's gonna give you some of the intersection points, but it may fail to give you a point like 0, because 0 has many representations, right? 0 has the representation where r is 0 and theta is whatever you like. Yes, so for example here, this 0 point in the cardioid in the cardioid happens when r is actually pi. So it is a point with coordinates 0, comma pi, if you think about it, right? So when theta is pi, cosine of pi is -1, -1 plus 1 is 0. But in the circle, it is a point with coordinates 0, comma, and pi over 2. Pi, no, not, yeah, pi over 2, right? And so you see the thetas don't match, right? It's not the same theta that gives the same r. And that only happens for 0, but that's one possible difficulty. Other difficulty is that remember that in pointing polar coordinates can have many representations. It can have not only that the angle is cyclic, but also that you can do the negative of it. You change r to -r, and then add pi at 180 degrees, and then you're back to where you started. So this is, I just wanted to let you know that you need to be careful. So it helps a lot to actually sketch the graph to figure out an idea, right? So in this case, we at least have the right idea that this point is now correct. Okay, so now let's set up the area. So how will we do the area of A? So area of A, it has to be an integral, right? It's like this. So 1/2 of the initial to the ending one. So the initial is 0, and the ending one is pi over 3, this ray over here. And then it's the outer function. The outer function is the one that you find farther away. In this case, is the circle. So it's the outer function square minus the inner function d theta. All right, and that's it. This is the calculus part, the new part that we learned. The rest is just to do this integral, right? So that's that. This next part should be now routine for you guys, because we spend a lot of time honing our integral skills, right? So we need to square these. It will be 9 cosine square minus parentheses 1 plus 2 cosine theta plus cosine square theta. Then we can combine these. 9 minus 1 is 8 minus 2 cosine theta minus 1. Next, replace cosine squared by cosine 2 theta plus 1. Divided by 2. And let's see. This is now 8 over 2, that's 4. So that's 4 cosine 2 theta. Then we have -2 cosine theta. And then the independent term is 8 times 1 over 2, that's 4, plus minus 1, 3. So 4 minus 1, 3, yeah. Good. I think we're ready to integrate. Okay, the integral of cosine is sine, and it has a 2 theta, so we should divide by 2. So this will be 2 sine 2 theta minus 2 sine theta plus 3 theta. And we're doing this from 0 to pi over 3. And now it's just a matter of plugging our numbers, right? So it's 2 sine of pi, 2 pi thirds minus 2 sine of pi thirds plus 3 times pi thirds, that's pi. minus, and then plug 0, 2 sine of 0 minus 2 sine of 0 plus 3 times 0. Okay, everything here is 0. You don't need to simplify it. Maybe this time we don't do, well, let's check. These are all zeros. And sine of pi over 3, that's 60 degrees. That's square root of 3 over 2. And the sine of 2 pi over 3 is the same. This is, so this is 2 times square root 3 over 2 minus 2 times square root 3 over 2 plus pi minus 0. This guy go away, and the answer is just pi over 2. All right? Okay, questions? Good. So maybe so we'll check the others now, and maybe we'll just set up the integrals, or well, actually, well, we'll see about the other two regions. So the rest of the problem is to figure out regions, the other regions. Let's go back to the figure. So for the rest, the other parts of the problem is to figure out this one. That's B. So that's the region inside the circle, and inside the cardioid. And the last question is this other region over here, which we call C. All right. Now, what would be the best way to do B? Given that we already did A, what would be the best way to do B?
Can you do area of half a circle and subtract A?
That's correct. That's exactly correct, right? Like Michael just said. So what we can do is take the area of this half a circle, which is easy, right? We don't need to do any integral for that. And then just subtract the area of A. So let's just, I mean, we could do it with an integral as well, but that would be, you know, like doing extra work. So let's set it up. Let's set it up the easy way. So the area of B should be to simply do the area of the semicircle. Remember that the diameter is 3 minus the area of A, right? And what is the area of a semicircle? Well, it's the area of a circle is pi r squared, right? And this is half a circle, so it will be half pi, and the radius is 3/2, right? And then subtract the area of A, which is pi over 2. So this will be, what is it, 9 pi fourths minus pi over 2. So that's 9/8 minus 4/8. That's 5/8. Okay, so but let's imagine that we're not that smart, and we want to set it up as an integral regardless, right? So then what type of integral would it be? Let's go back that way. So let me put just the picture here, right? So if we wanted to do it as an integral, what integral would it be? Well, let's see. We would actually need to do two integrals. One from here to here of this part of the circle, and then one from here to here to 90 degrees, right? From here to here. That's not that good. From here to here to do this little sliver of this orange part over here, correct? So the two integrals that we would need to do, let me write them over here. The first one would be 1/2 from 0 to pi over 3, right? So it's again this purple race that I drew before. But now the outer function is the circle, and there is no inner function. So it's simply the outer function is the circle, and that's it. And then plus, I would need another integral, this time from pi over 3 to pi over 2. And this other integral, we would need to do it from here to here. And we only care about this little blue part over here. So that's also the circle. So it's only the circle. Actually, hold on a second. Like, why am I breaking it like this, right? I don't need, yeah, I don't need this. No, I don't need it. My bad. So it's not the circle, right? I'm doing something wrong here. Yeah, okay. I realize my mistake. My mistake is that, well, the first one that we do, this is not the circle. This is the cardioid, right? This curve over here is the cardioid. So we're using the cardioid, which is 1 plus cosine theta. And then after we cross this point, now we use the circle. So now it's the circle from, and there is no other function. So it will be this one, okay? So that would be the way of doing it directly. And again, why do all that work, right? If you see we're involved doing two integrals, when we already did it, we could do it with this smarter way of figuring out the area of half a circle and subtracting the orange part. So that part, I'm not gonna do it. So I just wanted to, show you the integrals so that you can appreciate those. Instead, what I want to do is move on to the region C, right? How can we do region C? So what would be the area of C? All right. So for the area of C, we'll maybe I should do another picture here. Let me redo my picture so that we can, look closely at that part. So I'm gonna do it right here. So we have our cardioid. I'm gonna make it bigger this time. So here's one, and then we have the cardioid, and this grows. And I don't care about that part anymore. And then we have the circle. So the circle is of radius 3. And we knew this was the rate pi over 3. Okay, and then we want to figure out this area over here. And I hope you appreciate that we actually need to break our integral in two pieces. One going from pi over 3 to pi over 2, because on that one, we do have an outer and an inner function. So we go from here to here. The outer function is the cardioid, and the inner function is the circle. But then from pi over 2 to pi, which is where the cardioid finishes, right? Pi over 2 to pi. We don't, the circle plays no role, right? It's only the cardioid. So it's only this little piece of the cardioid that matters, okay? So let's set it up. Let's set up the integral. So the area of region C should be 1/2 the integral from pi over 3 to pi over 2 of the outer function, which is in this case the cardioid, minus the inner function. Plus, now this little piece, this little part of the cardioid where the circle is not involved, And that happens when we integrate from pi over 2 to pi. And it's only the cardioid, so it's only 1 plus cosine theta squared. All right? And I'm gonna leave it there. I'm not gonna try to do the integral. You can do it. It's nothing fancy. So you need to expand the squares, and there will be a cosine term and a cosine square term. And the cosine square term, you need to use the half angle identity to change it so that you can integrate. All right. So the important part here to me is to actually set up the integral. So I will leave it there for you. Because I want to go to the next thing, which is the length of a polar curve. And that's the last calculus topic we want to talk about. In fact, it will be the last topic of this chapter. So after that, we'll move on to something else. So we want to talk about arc length of polar curves, right? Specifically, so if we get a curve that is given by, like, say, one of these nice spirals, given by a polar equation, right? Some r equals f of theta. So how can we get its length? How can we calculate its length? What is the length of the curve r equals f of theta from theta equals alpha to theta equals beta? Right. That's the question. And it turns out that we already have the tools to answer this question in pretty much, I mean, there's a little bit of work involved, but not a lot. And that's because we already answered this question for parametric equations. So we already did this for parametric equations. Let's do it here. For parametric equations, here we have x equals f of t, y equals g of t. Then the length from t equals a, from t equals b, was the integral from a to b of dx dt squared plus dy dt squared, the square root of that. Or in other words, take the square root of the derivative of f plus the derivative of g. Right? So we had done that for parametric equations. So all we need to do now is to figure out the same trick we did for doing the derivative. We need to figure out how a polar curve can be transformed into a parametric equation. And that's easy because all we need to do is know how we can get x and y from polar equations. So x and y from polar equations are given by x is r cosine theta and y is r sine theta, right? But r is a function of theta. So then what we get is x is f times cosine and y is f times sine. So then the length we're looking for is simply this, the integral from alpha to beta. So now the only distinction is we're using theta instead of t, right? It's a parametric equation on theta. So here we ask that theta is a number between alpha and beta. So now our integral will be from alpha to beta. And what we need to do is take the derivative of x with respect to theta and square it, and the derivative of y with respect to theta and square it, and then integrate with respect to theta. Okay, and here I'm gonna do the work because this, so there's a little bit of work that I'm gonna do right now, but this work only needs to be done once. Then we're gonna get a formula, and you can you can figure out, you can use this formula all the time. So what is the derivative of x? It's right here with respect to theta. Well, we use a product rule, right? So it's the derivative of the first times the second plus the first times the derivative of the second, which is sine theta. So this will be minus, and we square that. And then here is the derivative of the first, that's f prime, times sine plus f times the derivative of sine, which is cosine. And we need to square it, right? It looks like a big and complicated expression, but actually it's going to become so much better. You'll see in a moment. See, when we square these, it's going to be the following. It will be f prime cosine square minus 2 times f prime f sine and cosine. So it's the product of this times that. And then plus the square of this, f of theta square sine square. All right, I'm done doing this first part. Now for the second part, I'm gonna put it in the bottom so that you appreciate what is it that I'm doing. So now it's the square of this one. So it will be f prime square sine square. Then the double product, but it has a plus sign over here. So it's gonna be 2 times f prime theta, f theta, sine, cosine. And then plus the square of the last one. There's one gigantic square root behind all of that. And I chose to do it like this, you know, putting one below the other one, so that you could appreciate the following. First, that this big term cancels, because it's the same, but one is negative and the other is positive. And second, that here we can factor the sine square and the cosine square. We can factor the f prime theta square from both, and sine square plus cosine square is equal to 1. All right, so this will be f prime theta square times sine square plus cosine square plus f of theta square times sine square plus cosine square. And this is 1. So is this one. So that complicated formula becomes actually quite simple. So the length will be just the derivative of f prime square plus the derivative plus the original function square. And that's it. That is it. Right? So this is the formula that you can now learn. You don't need to do this work all the time. You can simply remember that is this is the derivative square plus the original function square, the square root of that. So setting up the integral is easy. What could be a little bit harder is to do the integral, right? Because it involves a square root, right? And square roots are generally difficult. So let's do an example. This is example 7. It says, find the arc length of the spiral. Let me show it on the book, because the pictures are always nice here. So this is a formula we just discovered right here. So the arc length is given by the square root, the integral from alpha to beta of the square root of f of theta square plus f prime of theta square. And then the example we want to do is this one. We want part A to find the arc length of the spiral r equals theta from 0 to 2 pi. And I wanted to show you the picture. So it's this piece of the spiral, right? That spiral over there from 0 to 2 pi. So in this case, f of theta is just theta from 0 to 2 pi. All right, so let's switch to the paper and work the integral. So this is the length we want to do is the integral from 0 to 2 pi of the derivative square plus the function square. That's our formula, right? And that would be the derivative of theta is just 1. So so that's 1 square. And the original function is theta, so that's theta squared. Right? So as an integral, as setting up the integral, we're done. And this was really easy. It's just the integral of theta squared plus 1. Right? Now the problem is we need to do that integral, and that can be complicated. Right? In this case, it requires a trigonometric substitution, right, to do this integral. The trigonometric substitution you want to do is theta equals, we usually use theta, so this time I'll change it a little bit. I use t, so theta equals tangent t, so then d theta is secant squared, and then my integral becomes tangent squared plus 1. Let me just steal, this is t, sorry. Let me still mark it from 0 to 2 pi. I don't want to change the parameters because it will be easier if we don't. And then d theta, and d theta is secant squared, right? And then remember that tangent squared plus 1 is secant squared. And with the square root, this becomes secant cube. So this is the integral of secant cube from 0 to 2 pi. And we had done secant cube before. I'm not going to do it again. That takes actually a little bit of time. You need to do integration by parts and then know the formula for secant. So what I want to, I'm just going to go towards what the answer to this is. So the answer to the original one is, the original integral is theta over 2 square root of theta squared plus 1 plus a half of ln of theta, absolute value of theta plus theta squared over 1. And we want to do this from 0 to 2 pi. Okay. Now, when you plug 0, this is 0, and this is ln of 1, which is 0. So we only need to plug 2 pi, and that will be 2 pi over 2. That's pi. Square root of 2 pi squared plus 1 plus a half of ln of pi, 2 pi plus 2 pi squared plus 1. All right. So again, the point is the integrals that you encounter may be difficult, but getting the integral that represents the arc length should be easy. So there's nothing new here. We know that integrals that give you the arc length of something are difficult because they have the square root. Okay, so nothing is new with respect to that. Okay, and then just to finish it off for today, at least with the material, then maybe we can take a look at some questions. I want to do part B. So for part B, let's go back to the book, is now the integral of the arc length of the cardioid, right? This cardioid that we have been playing around for some time now. Now we want to find out what the length of it is. So the length, so this is part B. We want to do the length of r equals 1 plus cosine theta, the cardioid that you see on the screen, from 0 to 2 pi. Okay. Let's switch to the screen and do it. So How do we do it? Well, let's set it up. Will be the integral from 0 to 2 pi of the derivative square plus the original function square. What is the derivative of this? The derivative of 1, nothing. The derivative of cosine, negative sine. So it's negative sine square plus the original function square. Correct? So this now becomes sine square plus 1 plus 2 cosine theta plus cosine square. And sine square plus cosine square is 1. So the integral that I have is 1 plus 1 is 2 plus 2 cosine theta. Right, and again, like we've been saying all the time, these integrals are in general hard, right? Because we have the square root, and this is no exception. So this is actually a difficult integral to do, right? At this point, you can get puzzled and don't know how to continue. So there's a trick involved here, and it's actually kind of like the same thing we've been using all the time. So we want to use the half angle formula, because if you remember, for the half angle formula, so let me put it right here, or should I put it right here? So we know that cosine square of theta is cosine 2 theta plus 1 divided by 2. So this time we want to use it kind of like backwards, because this is kind of like cosine plus 1 once you factor the 2, right? If you factor the 2, this is 1 plus cosine. And so it looks a lot like this one, although you know it says theta, it doesn't say 2 theta. So that suggests that the identity we want to use is by replacing theta by theta over 2. So let me write down the one we need. The one we need is actually this one over here. Cosine square of theta over 2 is cosine theta plus 1 divided by 2. So that's what we're going to do. We're going to replace cosine 2 theta plus 1, this part, cosine theta plus 1, in here using this formula. All right? So here we go. We're going to get the integral from 0 to 2 pi, square root of 2 parentheses, and then instead of writing 1 plus cosine theta, we're going to write 2 times cosine square of theta over 2. Okay, and that's awesome because now we have a square and we can cancel the square root, right? This is now 2 cosine theta over 2, everything square. So the square cancels the square root with an absolute value sign. And we are not too bothered by the absolute value sign, because cosine between, when theta goes from 0 to 2 pi, theta over 2 goes from 0 to pi. And between 0 and pi, cosine is positive. So we don't need the absolute value bar, and that makes us even happier. So this is simply 2 cosine theta over 2. And that's great, because now we can integrate. The integral of cosine theta over 2 is sine theta over 2 times 2. And we want to do this from 0 to 2 pi. So this is 4 sine of 2 pi divided by 2 minus 4 sine of 0 divided by 2. And sine of pi is, I'll do this right. Hold on a sec. No, I didn't do it right. Yeah, my problem is I told you a lie right here. From here to here, I told you that this is positive, but that's not true. Cosine is positive from 0 to pi, not from 0 to 2. So from 0 to pi over 2, the regular cosine is positive. So right here, this is not correct. So what we can do from the get-go is, instead of doing the entire cardioid, so let me go back to the picture. See, this is the diagram what we're trying to do. We can use the symmetry, right? By symmetry, we can do it from 0 to pi and then multiply by 2. And so that's what we're going to do. Let me go back to the page. So let's use symmetry. And so by symmetry, really the one we want is from the very top, we want to put 2 times and do it all the way to pi. So it will be 2 here and a pi here. Okay, the alternative, if you don't want to do this, it's difficult because then when you get the absolute value, you need to differentiate on when this is positive and when this is negative. And I'd rather not do that, right? So this using symmetry is always a helpful thing. So we'll do it 2 times from 0 to pi. And so then this will be now 4 over here. This 2 and that 2, it's now a 4. And we're evaluating it from 0 to pi. So it will be 4 times sine of pi over 2, 8 times actually, minus 8 times sine of 0. And sine of pi over 2 is 1. So the answer, believe it or not, is 8. The perimeter of that cardioid shape is 8 units. It doesn't have anything pi or anything. All right. That's going to be it for what we're covering today. We still have about 15 minutes or so. So I wanted to start reviewing about our exam tomorrow, right? So as I have told you before, we're going to put it on Canvas. It will be available at 1 p.m. tomorrow, and you're gonna have 24 hours to do it and upload it, all right? Take into consideration the time it will take for you to upload it, all right? And the exam covers from chapter, essentially chapter 11 and chapter 12, but there were some sections we did not cover, right? So it's 11.1, 11.2, and 11.3, I believe, and chapter 12 is 12.1 to 12.3. We're not doing 12.4. 11.1 through 11.4, and then chapter 12.1, 12.2, and 12.3. So as is customary when we prepare for our exams, what we take a look is at the sample final exam, which you can find on our Canvas page. I'm gonna project it on the screen shortly, and just take a look at the problems that correspond to the sections that we want to cover. So you see it on the screen right now. So you should look at the problems starting from problem 18. So 11.1, then it comes 11.2, 11.2, 11.3, 11.4. And then we have 12.1, 12.2, and 12.3. Right, here are some figures about calculating the area of polar curves. And this is not included anymore, right? This is chapter 13. So that's beyond. So you should take a look at problems from 18 to 27. 18 to 27. So that's what I want to do right now. And I want to start with, well, we'll go in order, right? So from section 18, problem 18 and problem 19. At the same time, if you have any questions right now, so I'll gonna just open up your microphone and ask a specific question. That's perfectly fine. And you know, let me know about anything here, any questions that you may have. Okay. So let's start with 18. So in 18, it's about the quadratic approximation. So for quadratic approximation, what we mean is the Taylor polynomial, right? So what is it that you want to know for Taylor polynomial? You need to know the formula for Taylor polynomials. And it's the same as the formula for Taylor series, by the way, with the only difference that for Taylor series, you let it go all the way to infinity. For Taylor polynomials, it just stops at a specific point. So what is that formula? Let me put it on the screen. In fact, let's see if I can do this. So here's the formula you want to do for the Taylor polynomial. The thing you need to remember is that the Taylor polynomial Pn of x, centered at 0, is given by the kth derivative evaluated at a divided by k factorial x minus a to the power k from 0 to n. All right, so this is what we need to do for this problem over here. So if you take a look at problem 18, for any of these, we need to use a particular a, right? So it says, and use it to approximate the given value. So on a and b, when it says at x equals 0 or at x equals 25, that means the center of the approximation. And over here it says at a equals 1. So that's the center. That's the a value. And right now it only says quadratic. So we only need to do P2, right, all the way to n equals 2. All right. So just to give ourselves an idea of how to do this, let's pick B, for example. So let's work on B. So for B, what we know is that n equals 2. So n equals 2 and a equals 25. And our function f of x is square root of x, or x to the 1 half, right? So let's write down the polynomial P2. Let's make it bigger now. Okay, so the polynomial P2, what we need to do is just copy this formula. So it will be f of 25, right? Plus f prime of 25 divided by 1 factorial x minus 25 plus f double prime of 25 divided by 2 factorial x minus 25 squared, right? Should be easy. And so all you need to know is do the derivative and the second derivative of this function. Maybe we do it here. So f prime is 1/2 x to the negative 1/2, and f double prime is negative 1/4 x to the negative 3/2. And then we should plug 25, right? So f of 25 is 5, square root of 25. F prime of 25 is 1 over 2 square root of 25. So that's 1/10. And f double prime of 25 is negative 1/4 of 1 over square root of 25 to the cube. So that's 125. So the square root of 25 is 5. 5 to the cube is 125. And times 4, that would be 500. All right, so we're good. We can now write it here. So it will be f of 25, that's 5. F prime of 25, that's 1/10. And f double prime of 25, that's negative 100, divided by 2 factorial, that's negative 1000, times x minus 25 squared. So that's it. That's the answer to finding the polynomial. Now the second part of the question said use it to approximate. Let's see. It said use it to approximate square root of 28. So how do we do that? Well, that's easy. We just plug 28, right? So square root of 28 by definition, it's approximated by P2 of 28, and P2 of 28, according to the work we did, is 5 plus 1/10, 28 minus 25, minus 1,000 of 28 minus 25 squared. And I know you can see the, okay, let me move it a little bit this way. Okay, good. And so what is this? 25 minus 28 minus 25 is 3, so that's 3/10. And this one is 9. So this is a number we can figure out, right? It's 5 plus 0.3 minus 0.009, right? It's a number that we can calculate with relative ease and, you know, get a decent approximation. Okay, so that's a sample of this first problem, 18. The others are similar, and if you think about it, this is these problems over here also help you for Taylor series, right? Which is where you don't stop at 2, but you keep going all the way to infinity. And many of these series, for example, now in retrospect, this part C is easy because we even know the arctangent series, you know, from 1 to infinity. It's one of those series you should memorize, you should know already on the top of your head. So then doing part C should be easy because instead of using the entire series, we are you can only take the first 3 terms: the zero coefficient, the linear coefficient, and the quadratic coefficient. Okay, so we're running out of time, so I'm gonna stop soon. But I just wanna tell you how we're gonna pick it up tomorrow. So tomorrow during our class time, we'll review. Make sure you bring your questions if you have any, and that you can ask. And if not, well, we'll go over your questions, and then I'll pick selected problems from this sample exam, and we'll work on them. And so to begin with, we'll start with 19. And for 19, it's about finding part A, B, and C. The first part is about finding the radius of convergence. We know that for that, our tool is the ratio test. So that's what we should apply all the time. And then the last 3 are about finding the interval of convergence. And for those, you first find the radius of convergence using the ratio test. And then you check the endpoints. And when you plug the endpoints, you then go back and use all the material we know from regular series to find out if they are convergent or divergent. And that's the way you can determine the interval of convergence. Okay? All right. Any questions before?
Professor, can you go back to the problem you just did? We weren't able to see the last part.
Absolutely. I'll put it on the screen in a moment.
Yes, we're good now. Thank you.
Okay. Yeah, let me know, because I was trying to split the screen and show different things at the same time. And I think what I see on my screen was not exactly what you guys were seeing. So if anything like that happens, let me know. Any other questions? Yeah, someone, Matt asked about your grades from previous exam. Believe it or not, I'm still not done grading those. It takes a lot of work to do this virtual way of teaching, uploading your videos and all of that. Takes an inordinate amount of time. So be patient. You will eventually get them. The scores will be posted. Okay, guys. So I'll see you tomorrow for the review. Start studying. Bring your questions and start getting ready. Okay.